Let's say we have two bowling balls of equal mass. One bowling ball is on top of the table, and one bowling ball is on the floor. And I ask you, which bowling ball has a greater potential energy? And since they have the same mass, the same gravitational field acting on them, the only difference is their height. The bowling ball that is higher up would have the larger potential energy. What if instead of bowling balls then, I show you two marbles, one on top of a table and one on the floor, and I ask you which one has a larger potential energy? Well, you'd use the same argument and say that the marble that is higher up would have this higher potential energy. And no matter what object, as long as they're the same mass, you'd always say the one higher up has a higher potential energy. Well, what if there is no object at all? And I ask you, which location has a higher potential? Well, there is no energy because there is no mass, so you can't talk about its energy. But I think we can all say that just by being at a higher location, it has a higher potential of some sort. And we see that the gravitational field, and this is going to be important later on, the gravitational field points towards the lower potential, whatever that type of potential might be. Now let's go and actually apply this now to electricity. So now instead of a table, we have two charged plates, a positive and a negative. Now again, just by being higher up, we say that that has a higher potential of some sort. There is no charge in this situation, so there is not a potential energy, but it's a higher potential. And the electric field, in this case not a gravitational field, but the electric field points towards the lower potential. Again, it's not an energy because there is no charge, but it's a potential of some sort. We call this the electric potential. And we abbreviate the electric potential with the symbol V. Now, the only difference between this and the actual potential energy is that the potential energy had a charge located within this electric field. So the electric potential is really just the potential energy with one of the charges removed. Now, we had two equations for potential energy. One of the equations was the opposite of Q, E, D. And it was really more so the change in potential energy that was more important, but we'll get to that in a little bit. But the potential energy, if we divide by one of the charges, we're left with the electric potential simply being the opposite of E times D. And the other equation for potential energy is if we were given two charges, it was K, Q1, Q2 over R. And so our other formula would be divide by one of the charges, KQ over R. Now again, like we said before, it's mostly the change in potential energy that's important instead of the potential energy itself. And it's the same situation here. It's the change in the electric potential, also known as the potential difference, that is more important than the electric potential itself. And so the potential difference would be the opposite of the electric field times the distance between the two plates. Or, because if the other charge is at 0, or if the other location, I should say, is at 0, because when when the other location is infinity, when R is at infinity, our electric potential is 0. So this potential difference is still KQ over R if the other location for R is at infinity. So that equation actually does not change. Now, this potential difference is also known as the voltage. And so we're going to eventually talk about how this is applied to batteries, because most people think about batteries when they think about voltage and that application. Now, again, there is no charge in this location, so we can talk about the voltage of a battery without any kind of a charge being connected to the battery. But if we do put a charge within these two plates here, what's going to happen is a negative charge moves towards the positive or higher electric potential, and a positive charge will move towards the negative plate or the lower electric potential. So electric potential is the potential energy per unit charge. And so our original equation is V for electric potential is equal to the electrical potential energy divided by the charge. The units then would be a joule, energy is joules, divided by a coulomb. And that comes out to be a volt. More so than the electric potential, it's the change in or the potential difference that's important. We also refer to this as the voltage. Positive charges tend to move towards lower electric potential, and negative charges tend to move towards higher electric potential. And our two equations for voltage, or potential difference, is that voltage is kQ over R if the other distance is at infinity, or voltage is the opposite of the electric field times the change in displacement, the distance between the two plates.